Hi, my name is Matthew Yahov, and today we're going to talk about Versa QoS. So first of all, QoS Basics. Why do we even need quality of service? Imagine a situation when you have two clients on one side and on another side. They are connected using 100 megabits link to their border router, and the routers are connected with also 100 megabits link. Now, if these two clients will try to exchange information on the maximum speed they can, for example, sending some file, we don't have any problems, so the situation will not have any issues at all. But if, for example, the connectivity between routers is going to be smaller, the speed of the connectivity is going to be smaller than the connection from the clients, that's where we might have problems. Because if we will try to send the data with the maximum speed, we'll have a bottleneck between routers, and there's definitely going to be some drops. The same situation might be when you even have, like, let's say 100 megabits connection between routers, but you have multiple clients, each of which connected 100 megabits per second. They might also try to send information to the other side, but because they all sharing one link between routers, there might be problems. So the main task of the QoS is to address the problems with the oversubscription of the links and to make sure that we pass the most interesting or most valuable traffic first on the line. So which tools QoS provides us to address the bottleneck situation? The first tool is the prioritization. You can define certain type of traffic and say that that traffic should always be prioritized and sent to the link first. For example, we really care for the voice traffic and we want to make sure that it's going first to the WAN link. So we can say that voice queue and all traffic that is classified as the voice should always go first. Additional feature which we can do with the QoS, we can decide, for example, what should be the ratio of different types of the traffic. For example, we can say that the ratio of the packets that are being sent from the FTP and HTTP traffic and scavenger traffic should be 2:1. So which means that, for example, we want to send for every 2 packets that are sent from the FTP HTTP queues, we're gonna send 1 packet from the scavenger queue, and so on and so forth in the future. Another tool that QoS can provide us is the limitation of the traffic, and there are 2 main mechanisms which we can use here. First one is the policing, and second is the shaper. We can review both of them in much more details in the following slides. So let's continue. Policing, what it is, how it works, and how we can use it. First of all, policing usually works only for incoming traffic. So there are rare cases where you would configure policing on the egress, so in most cases it's only for incoming. It will drop everything above the defined threshold. So let's assume that you have a 100 megabits interface and you have some traffic going. So if you will enable policing, let's say to 50 megabits per second, it will drop all the exceeding traffic. Every single packet that is exceeding the defined policing limit will be dropped. This method is good for use for voice traffic, for streaming applications, games, video, and so on. So the second type of limitation is the shaping, and the shaping works similar to policing, but there are a couple of very distinctive differences. First of all, shaping can only be applied on the outgoing interfaces, so you cannot shape traffic which is coming into your router. You can only shape the traffic that is going out of your router. So that's the first thing. Second, Shaper is not trying to drop packets. Instead of trying to drop the exceeding limit, it just queues it for the future use. So all the traffic that is exceeding the defined limit can be queued for later periods of time. So let's take an example of how shaping is going to be working. In this example, we have one queue that the size of that queue is 10 packets, and we're doing shaping to 3 packets per second. By the way, shaping can be done in packets per second or bits per second, so it's up to you how you want to configure it. Now, let's assume that in the first second we got 4 packets in the queue, which means that based on the shaping configuration we can send out 3 packets on the wire. So we send 3 there, and we cannot send anything else within that second. Now, during the second second, we got another 4 packets. So again, we can send only 3 packets on the wire, but the others, which we couldn't send because of the shaper configuration, they are queued for the future use. On the third second, there might happen that there won't be new packets at all, so we can just send out the remaining packets and that's it. And therefore in the first packet we can get more packets and so on and so forth. Now let's take another example. So let's say that you have the same configuration with a shaping which is configured to 3 packets per second, and for some reason we got our queue full. So we have all 10 packets in the queue already. What will happen if we will get the 11th packet? So that packet is going to be dropped, and this kind of drops is called tail drop. Tail drop is when you have a full queue and therefore all new packets are being dropped, which means the behavior is going to be exactly the same as in case of policer. So the tail drops are bad, and to avoid situations like tail drops, we have a couple of mechanisms. They call it WRED and WRED. RED stands for Random Early Detection. In case if we have some packets in the queue, we can decide or define in the configuration for the queues that we can randomly start dropping packets which are being queued starting from a certain threshold. Let's say that in this case the threshold is 5 packets. So which means that if we have a queue consisting of 1 packet, everything is good. If we have 2 packets, everything is good. But if we are going to the packets, like to the 5 packets, everything is good as well. But the packet number 6 or 7 most probably are going to be dropped, because we are trying to minimize the tail drops in the future. We want to signal applications that they need to start sending traffic a little slower. And specifically for these purposes, we're randomly dropping certain packets after a certain limit. Now let's review the advanced version of the WRED, which is called WRED. The WRED is like the enhanced version of the random early detections, which allows us to have multiple types of traffic within the same queue, and we can assign different behavior of the random early detection for each of the classes. In this case we call them weights. So we can say that, for example, we're gonna assign all the traffic, all the web traffic and all database traffic to the certain queue, and we can say that we want to start randomly dropping HTTP packets when the queue size is 5 or more packets, while we will start dropping database packets when there's going to be 7 or more packets in the queue. Which means that behavior is going to be, we receive certain number of packets, so there is a congestion, therefore they are in the queue, and we have 5 packets. Nothing is being dropped, we are safe in this case. But if there's going to be more packets, let's say there's going to be 5, 6, 7, 8, 9 and so on, the yellow packets, HTTP, will start being dropped when there are packet number 6, 7 and so on. The database traffic, the blue, will start being dropped only when the queue size will be 7 or more packets. So we have the weights for the drop profiles in this case, and that's what is WRED. So basically the only difference is that we can assign multiple types of traffic to the same queue and drop them differently. Now let's go to the last feature that QoS can provide us, and this feature is the classification. Classification can be done in a couple of different ways. So first of all, for classification of the packets, so that system can decide where the packet should go, we can use a DSCP field in the IP header. This is a special field that was purposely created for QoS operations. Based on this field, devices can make a decision into which queue the traffic should be assigned and how it should be treated. There is a similar field in the layer 2, which is called 802.1p. This one is in the VLAN header, but it's not that commonly used. It is the best practice to do classification and assignment of the DSCP class as close to the source as it's possible. Let's take an example. So we want to transfer one packet from the client on the left to the client on the right. We have a packet. We send it to router 1, and router 1 is doing classification. So he sees that this is the packet of the voice type. So he will rewrite the DSCP value of that packet to the value 46. This is the most common DSCP value that is used for the voice traffic, but it doesn't mean that it has to be this one for the voice. You can have any values for any packets. You can have even 0 value. It's still not going to change a lot. Anyway, so in this case, we decided that the voice traffic should be assigned the DSCP marking 46, so it will change the IP header of the packet to the value 46 in the DSCP field. Then we're gonna send out this packet to the next router. The next router can do classification based not on the D packet inspection to identify that it's voice traffic, but it can just look in the DSCP header, which is much faster, and can identify that based on the DSCP header, I'm gonna assign it to a certain queue, for example to the fast queue to fastly process the voice traffic. Then it sends the traffic to the packet to the next router. The next router, he may trust the DSCP marking, or the next router might even say that I don't care about DSCP values, just send it out as the rest of the packets without any priorities. If you're sending traffic through the internet, that is going to be the case on every single router like that. So internet doesn't care about the DSCP values, and usually that is something that is used in the private networks such as MPLS connections or your local connections. Okay, anyway, so after that point, we can send traffic next to the next router. And the next router can either trust those values, or he can say that I don't trust any DSCP values, I'm just gonna reclassify it again. So he will do the D packet inspection, look at the port, source destination, and so on and so forth, and will do classification and rewriting of the DSCP value to any value that he wants. For example, in this case, DSCP 32. And he will send out the packet to the end host. I purposely created this example with each router doing different operation. In the real life, you most probably gonna have the classification on the first router only, and all the remaining routers will act the same way if it's your private network. Like for example, all of them either trust those DSCP values or they don't trust any of them to the DSCP values. And now let's talk about the order of operations inside of the Versa system. So first of all, and the very first operation that is going to happen with every single packet is the classification. So we can classify based on the layer 2, layer 3, and layer 4 headers, and do classification based on these fields. Together with the first classifier, we're going to have a policer, which can police based on the same values as we just classified. But now check what is going to happen next. Next, we're going to have another classifier and another policer. Usually, classifier and policer goes in tandem with one another. This is due to the use of QoS profiles in the Versa operating system. We're going to come into much more details and review of both classifiers and both policers in details in the later on slides. The next operation is going to be the remarking operation, which allows you to rewrite DSCP values or .1p values of the packet. And of course, queuing and scheduling are going to be the follow-up operations. Now let's talk about classification, policing, and QoS profiles, which are used in both of these operations. First, classification. We have two classifiers. First of them is the flow-based classifier, and second is the session-based classifier. Classifiers can assign the flow or the session to one of 16 forwarding classes, from the forwarding class 0 to forwarding class 15. One of the main things to keep in mind is that flow-based classifier by default assigns all of the traffic to the forwarding class number 12. So if you don't have any specific actions to assign the flow to a certain forwarding class, it will implicitly assign it to the forwarding class 12. You'll just need to know this for the future because it's going to be used in a couple of examples. To make sure that you understand what is flow and what is session, we're going to take one example. So first of all, in this example, let's imagine that we have a client and a server. Client's IP address is 1111, server's IP address is 2222, and they are connected using Versa OS FlexPNF. Now, let's assume that inside of the Versa OS we have two interfaces, interface VNI00 and VNI01, and also we have zones, security zones internal and security zone external. Now, Client tries to establish a session. He sends a packet to establish the session, which crosses the Versa OS to the server. Server replies with a certain message acknowledging that the session can be established between the client and the server. So we have two ways of communication. One way of communication is shown by the light blue line, and the reverse direction shown by the yellow line. Now, if we're gonna check how each of them called, the light blue line represents the forward flow. The yellow line represents the reverse flow. And the dark blue line, which contains both of them, forward and reverse, is the session that is going to be established between the client and the server. And now let's see how both classifiers will work. First, flow classifier example. So let's say in this classifier we are making a match statement, which is saying that we want to match all the traffic that is coming from the zone internal, and we want to assign it to the forwarding class number 8. The final result is going to be that the session will have forward and reverse flow. The forward flow will become in the forwarding class 8, while reverse flow will stay in the default forwarding class number 12, because we matched only in one direction using the flow classifier. Another example, session classifier example. We're doing the same match condition in the session classifier. We're saying that we want to match all the traffic that is coming from the internal zone, and we want to assign it to the forwarding class number 8. In this case, the final result is going to be that both forward flow and reverse flow are going to be in the forwarding class 8, because it works on the session, not based on the flow. And lastly, let's review the case when we use both classifiers. We use both forward and reverse classifiers, and we use absolutely the same match conditions. So we're matching traffic, which is coming from the internal zone, and flow classifier assigns it to the forwarding class 8, while session classifier assigns it to the forwarding class number 9. The final result is going to be that both forward and reverse flow are going to appear in the forwarding class number 9. This is because the session classifier always takes action after the flow classifier, and it can rewrite what was already assigned by the flow classifier. So even though initially first classifier assigned the flow into the forwarding class number 8, session classifier, as it goes after the first classifier, it rewrote the forwarding class to the forwarding class number 9. And it rewrote actually both of them, forward flow and reverse flow. What are the main differences in the flow classifier and session classifier from the match condition standpoint? In the flow classifier, you can classify flow based on the source and destination zone. You can classify based on the source and destination IP address, port number, TTL value, DSCP value, IP flag, .1p value, MAC address type, and even ether type. That's all can be done in the flow classifier. The match conditions in the session classifier, the one that is bidirectional, are almost the same, but instead of layer 2 match criteria, we have layer 7 match criteria. So in here we can use actually DPI to match based on the applications and even URL category for your traffic. Let's see where we can find both of these classifiers in the Versa Director menu. So this is Versa Director, which I'm going to be using for this practice. In here we have a couple of templates, and let's select one of them. For example, template number 1. Inside of this template, we have the QoS configuration in the class of services menu. So here it is on the left. Inside of the class of services menu, there are QoS policies, and there is also another menu which stating application QoS policies. The first of them, just QoS policies. This is the flow-based classifier. If you want to classify only based on the flow with your match conditions, you can create a policy. Let's say that this is going to be rule 1 inside of this policy. We're matching based on the source or destination zone, or maybe based on the source or destination IP address. We can also match based on the port number with the with the well-known services names, or you can match based on the TTL. You can also schedule that, for example, you want to match only during night hours or day hours, or week hours, or maybe only weekend. And also you can match based on the layer 2 conditions. And of course you can then enforce assignment to the proper QoS profile. Both classifiers and policers work with the QoS profiles, which we will review a little later in this section. So the same if you'll go into the session classifier, which is located in the app QoS. And if we'll try to add the new rule, so let's say rule number 1. In this case, we also can match based on the source and destination zone. We can also match based on the port numbers like tuple 5 information. We can also do the scheduler to make this rule work only during certain hours or minutes. And also in this case, instead of layer 2 information, we have layer 7 information, where we can match based on the applications such as Facebook or maybe, I don't know, SAP and so on and so forth. So here's where you can match based on the layer 7 information, and of course you can assign it to the appropriate QoS profile to assign to the forwarding class. Now let's talk about policing. Policing, once again, as well as classification, can be done in 2 ways. It can be done based on the flow, or it can be done based on the session. We do not recommend to use multiple policers simultaneously on the same traffic. Now, just to demonstrate how the policer works, imagine that you have certain bandwidth and you want to police traffic to a certain value, which is represented by the red line. It means that the end result would look like this. So all the exceeding traffic will just cut it. Next, we can configure policing based on the peak rate, which can be measured in the packets per second or kilobits per second. You can see the menu of the policing configuration on the left. There is also a third parameter, which is called burst size or peak burst size. This is a low-level configuration. It's a layer 1 OSI model config parameter, which is measured in the bytes, and you should only touch it if you really know what you're doing. To give you a short explanation of what it is, imagine that we have a graph here. So we have a bandwidth in kilobits per second, and we have a time frame, let's say 1 second, because we're measuring everything in the packets per second or kilobits per second. Now, let's say that we assigned a policing limitation to 50 kilobits per second. The thing is, the data on the layer 1 is being transmitted in bursts. So it means that we're gonna have multiple bursts, and within a second there might be hundreds of bursts, it might be even thousands of the bursts. And when the traffic is going, we set the policing to be policed per second. It means that we shouldn't on average exceed the policing value per this second. But sometimes we might have bursts that can come unexpectedly and might burst a little more across the assigned threshold that we specified to be the policing value. And this specific parameter, burst size, allows us to specify how much we can exceed the specified limit within the measured parameter, in this case packets per second or kilobits per second. Also, one thing that I wanted to mention, that peak burst size cannot be shown in here in the value inside of the template. It cannot be shown because by default burst size on the 1 gigabit interfaces, 10 gigabit interfaces, 100 megabit interfaces, they're all different. This is a hardware parameter that is usually being assigned or being specified by the manufacturer of the hardware equipment. So in this case, there are always going to be some value implicitly assigned as the burst size. You should only modify this parameter if you know exactly what should be the burst size for your hardware device, for your interface card, or for your appliance to specify in this parameter. Now let's take an example of configuring policing. So we already reviewed the classifiers, the flow classifier that is going to be in the QoS policies, and we reviewed session classifier, which is going to be in the application QoS policies. At the end of the classifier, as you remember when we created rule, we had to assign a certain QoS profile. So the QoS Profiles, that's the section when you can configure, first of all, your forwarding class, and second, your policing rate. So let's go to the QoS Profiles section and create something. So we're gonna add, let's call it QoS Profile 1, and we can specify, let's say, the policing rate to be 100 kilobits per second. And also we can specify in here the forwarding class that is going to be assigned to that specific traffic. Let's say that it's going to be forwarding class number 9 with the lowest priority. We're going to talk in details later what is the lowest priority and the other parameters in here. For now, let's assume that we have specified only the policing rate and the classification to what of the forwarding classes we're assigning this traffic. So we're going to say OK, and it means that now when we actually create the new policy for classification, let's say that we're creating rule number 1, we're matching everything that is coming from the, let's say, our SD-WAN, and we assign it to the QoS profile number 1. So this means that all the traffic that is coming from the zone PTVI is going to be assigned to the forwarding class number 9, and it's going to be policed to 100 kilobits per second. To review in a little more details what QoS profiles are, imagine the following situation. We created QoS profile number 1, in which we specified that we want to police to the value of 20 megabits per second, and we also want to assign that traffic in the forwarding class number 7. And now, let's say that we're doing match condition based on the application Skype for Business, and we're assigning this application to the QoS profile number 1. So this means that all Skype for Business actions and all the flows forward and reverse, if we're using the application-based QoS, are going to be policed to 20 megabits per second in total. We can assign multiple different match conditions to this QoS profile. So we can create additional rule for the application WhatsApp and also use the same QoS profile. This will mean that both Skype for Business and WhatsApp, they are both policed simultaneously to 20 megabits per second. So if one of them is using 15 megabits, the other one will be able to use only 5 remaining megabits of the bandwidth. But what if we want to assign traffic to the same forwarding class, but we don't want to put the traffic in the same policer to be policed to 20 megabits per second together with the Skype for Business and WhatsApp? In this case, let's say that it's a Viber application, we can create absolutely new QoS profile. Let's call it QoS profile number 2. Parameters inside of it can be absolutely the same. So we can say to also police to 20 megabits per second and also assign to the forwarding class number 7. But in this case, Viber will get its own 20 megabits per second, while WhatsApp and Skype for Business will compete for the 20 megabits per second in their QoS profile. Another example. Let's say that for the ICMP traffic, we create a new QoS profile, which we call QoS profile number 3, and in this case, we're going to specify to police to the packets per second, not megabits per second. I just wanted to underline once again that we can police based on the megabits per second or kilobits per second, and we also can police based on the packets per second. So this is also a possibility. Another example. What if we want to assign traffic to the forwarding class number 13, but we don't want to police at all? This is also possible. In this case, you can just create the QoS profile number 4, which will not have any policing values, but it will have only the forwarding class assignment. And this is actually the way how it's done in most of the cases. Before we go to the next section, let's review another example. Let's say we have, again, client 1111, we have server 2222, we have Versa OS device, which has internal and external interfaces, but in this example, we will also have a tunnel interface. And we know that the routing table of the Versa OS device pointing to the IP address 2222 through the tunnel interface. Now, example, we configuring classifier which is matching all ICMP packets on the internal zone interface and assigns them to the forwarding class number 9. Now let's say that 1111 is trying to ping IP address 2222. So we have some ICMP packet which has some ICMP payload. It has the destination IP address and the source IP address. This packet is being sent to the internal zone or interface via 900 as it's our default gateway. And we're doing classification and assigning this packet internally inside of the Versa OS memory as the forwarding class number 9. Interesting thing, when the packet traverses next to the tunnel interface, it will be encapsulated into additional set of source and destination IP addresses which belongs to the tunnel. So technically, initial source and destination IP address are not visible, but the forwarding class inside of the system remains the same because we already classified this packet initially on the internal interface. So therefore, when this packet will move out of the box to the outgoing interface, the forwarding class will be still the same forwarding class number 9, which we were able to classify initially as the packet was ICMP. And of course, forwarding class can be used for scheduling, it can be used for prioritization and multiple other things. So now let's see how we can check actually how and what forwarding class and how the policing works for a particular session. For this, you can go to the monitor screen, and by selecting the branch you can check the sessions menu or you can check the class of service menu. In the sessions menu you can see information about the session like the forwarding class, the reverse forwarding class. In the class of service you can see information about the classification, about the policing and other parameters. So let's take an example. In our example, here's our topology. So I have two branches, branch number 1 and branch number 2. Also I have two clients, client number 1 and client number 2. So let's configure some QoS parameters on the branch number 1. For this, we're gonna go to the configuration on the director. Here we're gonna open the template QoS, which is currently used on the branch number 1. And here we're gonna go into the class of service parameters. And here we're gonna say that we create a rule number 1, which is matching everything that is coming from the LAN zone. And also this should be ICMP traffic. And we want to assign this traffic into the new QoS profile, which we're gonna call QP1, with the policing rate of 10 packets per second. And we're also gonna assign it to the forwarding class number, let's say 6. So we're gonna say okay, so we created this rule. Now let's apply our new configuration from the template QoS to the branch 11, or in this case branch number 1. Okay, it was assigned, and now we can go to the user number 1. On the user number 1, which is going to be one of the end machines. Okay, we're gonna launch the extern, and the IP address on this machine, on the user 1, is 10.10.10.100. If we're gonna open the user number 2 on the other side, and we will launch something like external. On this side, IP address is 20.20.20.100. So from the user number 1, which is located in here, let's try to establish a constant ping to the 20.20.20.100. So the ping is going. Now we're gonna go back to the Versa director, and here we're gonna go into the monitor screen. On the monitor screen, I'm selecting my organization, which is called Matthew. In the devices screen, I'm gonna select branch 11. And on this branch 11, we're gonna go into the sessions first. In the sessions, we can see that there are two active sessions right now. we can see that one of them is ICMP session, which is going from 10.10.10.10 and it's going to the 20.20.20.20. The protocol is ICMP. Here's information about how many bytes and was transmitted and received. And if we're gonna click on the I sign in here, we can see information that the forwarding class is FC6, forward forwarding class. If we're gonna scroll down, we're gonna see that the reverse forwarding class is also FC6. Now, if we want to see a little more details about the policing, we can go to the class of service section, and here in the application QoS policies or session-based classifier, we can see the default policy. And this default policy is using rule number 1, so we can see information about how many sessions hit it and if there were any drops because of our policer settings. So right now there was not a single drop. And therefore, let's try to generate some. So to generate some drops, let's use the parameter of the ping -i, which allows us to specify the interval between pings. So let's say the interval is going to be every, I don't know, 50 milliseconds. And the IP address, the destination is the same one, 20.20.20.100. So we start doing this and we're gonna see some drops soon. So we're gonna go into the class of services menu. In here we're gonna select the default policy. We can see that there are some drops on the line, and this is because of the policer. We cannot see information for which of the sessions we have these drops because it's kind of very hard to pull this information from the policer, but at least you can see if the rule that matched and that's supposed to be doing policing, if that specific rule is generating some counters in here for the policer. So now let's finally talk about shaping and queuing. We will begin with the overview of the forwarding classes. Previously, in the classification section, I told you that we have 16 forwarding classes in total. They are going from the number 0 to number 15. Logically, they all can be divided into 4 groups. Group number 1 is traffic class 0, then it's going to be a traffic class number 1, 2, and 3. By default, queues are only going to be used in case if we have some kind of a congestion. So if you don't have any congestion, if your line rate is enough for you to transmit all the data, you will never have any information in the queues, in the shaper, and so on. So therefore, let's assume that we have a congestion and we have some information that needs to be queued for a later transmission on the line. And each of the yellow squares represent a single packet. This means that the first information that is going to be going out of the box is going to be going from the traffic class number 0. This is called a strict priority of one class over another, because the next is going to go the information from the traffic class number 1. Only after all the information from all the queues in the traffic class 0 and 1 is going to be transmitted, only then the system will start trying to transmit something from the traffic class number 2. And only after it will try to transmit something from the traffic class number 3. Like it's shown here. But now, very interesting thing. This will only work if you will enable shaper and queues on the interface. By default, if you just assign some traffic into the forwarding class and you didn't enable queuing, this will do nothing. And the forwarding class will mean nothing. So forwarding class means something only in case if you enabling queues. Next, let's review this in a little more details. So we have 16 of the forwarding classes, which are divided into the 4 groups with a strict priority one over another. Each of these forwarding classes will be associated with the appropriate queue on the subinterface. So therefore, if we have 2 subinterfaces of a single interface, we will have 16 queues for one of them and 16 queues for another of them, with a mapping 1-to-1 from forwarding class to the queue that is going to be on the subinterface. So it might happen that you will have multiple packets that will be assigned to the same forwarding class, but they will end up in the completely different queues which belong to a different interfaces, because these will be assigned based on their routing, not based on the forwarding class itself. Now, in total, you can have up to 64,000 queues per outgoing interface, because you can have 4,000 VLANs if we'll include the extended VLANs, and therefore it results in 64,000. Now, second thing that you need to know, inside of the traffic classes, we cannot reassign forwarding class from one traffic class to another. So it's hard limited and hard coded this way that traffic class number 0 will always have only 4 forwarding classes, and therefore only 4 queues on the subinterface. You cannot add or subtract the queues from this traffic class. There is just no possible way to do this. Let's see how we can enable queues on the interface. So first of all, we will open the template QoS, which I'm using as my post-staging template for the devices. Inside of this template, we're going to go to the class of service section, and we're going to open the associate interface network. In here, and specifically in this menu, we can add new association, where we can specify that we want to create the association or enable queues on one of the interfaces, or we can also do this per subinterface based on the network. So if we're going to click on the network, you can see only networks. And by the way, as soon as you assign subinterface to the network, it will disappear from the interface section. Like for example, in here, you don't see any VNI 0 dot something. This is all because we have the networks which contain those subinterfaces, and therefore it's going to be shown only on the network. So if I want to enable the queues on the internet interface, I'm just doing this, and that's it. After that, the queues with the proper prioritization will work on this subinterface. Okay, so let's continue. Next, we support Hierarchical Shaper. This means that we can apply, or you can apply the shaper in multiple different places. First place, you have 16 queues per subinterface. There's always this number of queues. You cannot have more, you cannot have less on the interface. So you can apply shaper per traffic class. This is the first place where you can do this. On each of the traffic classes, you can shape to a certain value of your choice. Then you can also apply shapers per subinterface. So after you shaped each of the traffic classes, you can also shape the subinterface. And lastly, you can do shaping on the interface basis. The interesting thing here that you can use all of those shapers simultaneously. So for example, you can say that traffic class 0 is going to be shaped to 10 megabits per second to give some space for the others. Traffic class 1 will be shaped to the, 100 megabits per second. Subinterface will be shaped together into 200 megabits per second. So you'll have 20, 100, and the remaining is going to be divided among traffic class 2 and traffic class 3. Same way you can do multiple shapers on the subinterfaces and then shape it together to a certain rate on the interface basis. So where can we configure all of those shapers? First of all, you can configure traffic class shaping in the scheduler menu. So on the left in here, you can see the schedulers. You can create scheduler for each of the traffic classes, or you can create the reusable scheduler entries in here as well. So you'll have information about the transmit rate and guaranteed rate. So second place is the scheduler map. Scheduler map is where you combine multiple schedulers into one single entity, because you have schedulers only per traffic class, but when you want to assign them to the subinterface or interface, you need to create a scheduler map which will contain parameters for each of the traffic classes. And lastly, when you created your scheduler map and you want to actually assign the traffic class scheduling to the subinterface or interface, you will do this through the associate interface, and that's exactly where it's going to be this menu. which will allow you to do shaping and also specify the burst size for this specific shaper and this sub-interface or interface. Let's try to configure this. So we're gonna go into the template, and inside of the template, first of all, schedulers. So we'll create a scheduler, and let's call it TCX. In here, we can specify what is going to be the transmit rate and what is going to be the guaranteed rate. So if we're going to say that transmit rate is going to be, let's say, 1 megabits per second, and the guaranteed rate is going to be 500 kilobits per second. And we're going to say OK. Then we're going to create another scheduler, and let's call it TCY. In this case, we're going to say that the transmit rate is going to be 1 megabit, 10 megabits, 100 megabits, and the guaranteed rate is going to be 5 megabit. And again, we're going to say OK. Later on, we can go to the scheduler map. Inside of that scheduler map, let's call it SM scheduler map 1. The system offers us to assign different schedulers to various traffic classes. So for example, we can assign traffic TCX scheduler to the traffic class 0, then we can assign TCY to the traffic class 1, and the interesting thing, we can actually reuse schedulers later on. We can even create the configuration with only one scheduler for each of the traffic classes. So schedulers, they are kind of reusable, and you can reuse them however you want later on. So anyway, let's create some kind of a scheduler map, and later on, when you have the scheduler map configured, we have the interface. In this case, for example, INET, or actually let's create another record for the MPLS network. So for the MPLS network, and here, system offers us to assign one of the scheduler maps to properly schedule queues on the line for this specific interface. If you don't want to do shaping per traffic class, you can always do a common shaper only for this subinterface MPLS. And you can say that, for example, we're shaping to 110, 100 megabits per second, this MPLS interface. So you can click just OK, and in this case we just enabled shaper only for this subinterface. If we want to also enable shapers per traffic class, we can assign the scheduler map, and now it's also assigned in here as well. Next, if you want to assign shaper also based on the interface, for example interface VNI00, once again, not subinterface, but interface into which we're going to have multiple, like INET and MPLS, they're all going there. And once again, you can configure shaper in here. And you can say that it's going to be another, let's say 1 gigabit. So that's how to configure shaper on the Versa OS box.